Consider functions f and g. If I wanted to substitute a value into f or g, I would just simply replace the x value with the number I want to substitute into the function. For example, if I wanted to substitute the value of 2 into f of x, I would just simply put a 2 where the x is. So it becomes 2 plus 2 is 4. So the value of the function at 2 is 4. Likewise, we can do the same with g of x. If I wanted to substitute the value of 25 into g of x, wherever I see an x, I would simply just put a 25. So the square root of 25 is 5. Composite functions are just where we substitute one function into another function in the exact same way. So for example, if I wanted to substitute the function f of x into g of x, wherever I see an x in g of x, I simply put f of x. And in this case, f of x equals x plus 2. So how exactly does this work? Well, simply stated, what we're going to do is we're going to put x values into the function f of x, and these are going to output y values. We are then going to take those y values and put them into the g function, and those are going to output the final value, y dash. Take, for example, 14. If I substitute 14 into f of x, we get 14 plus 2, which outputs a y value of 16. Now, because we're substituting the value of f of x into g of x, I need to take that 16 and substitute that into my g function, which is the square root of x. So that becomes the square root of 16, and the square root of 16 is 4. If we look at the original function of g f of x equals the square root of x plus 2, if I substitute 14 into that function, we get the same value of 4. This can also work for other numbers like 2. If I put 2 into my f of x function, this becomes 2 plus 2, which outputs a value of 4. We then need to take the value of f of x at 2 and input that into the g function. So I put that 4 into my g function, which gives me the square root of 4, and the square root of 4 is 2. And again, if I simply put that into the stated function that we have above, g of f of 2 is going to be the square root of 2 plus 2, which again gives us the value of 2. So this chain works. Consider the value of negative 4. If I put negative 4 into f of x, I get negative 4 plus 2, which gives me negative 2. Then we need to substitute the value of negative 2 into the g function, which gives me the square root of negative 2. And this is where we come into a problem now, because we're going to assume that we can only accept real values for x and y. And obviously the square root of negative 2 is not going to be a real value. This creates a problem for us. Even if I substitute it into the function that we worked out earlier, we still get the same value of the square root of negative 2. So it can't actually handle this. So how do we go about approaching these types of problems where we can't just input any value of x into f to give us an output value for g? What we need to do is we need to make sure that what's coming out of f, so the range of f, is going to fit into the domain of g. So as it stands, the domain of f is going to be x is an element of the real numbers, and the range of f is also the y belongs to the set of real numbers. With square root functions, we know that we can only square root positive values or 0, and that will output positive y values only. So what happens is we're going to put these x values into our f function. That's going to give us the y values. That's the output of the f function. Then we take whatever comes out of the y values. So we're going to take whatever the range is in the f function, and we need to be able to input all those values into the g function, which is the domain of g. And then those values that belong to the domain of g will output some range of g. So that'll output the y values that we want at the end. But at the moment, we can see there are some values that we could output for f that won't fit into the domain of g. And that's illustrated by the previous example where we tried to put negative 4 into f of x. It did work for f of x, but it didn't give us any values for g at the square root of negative 2. So obviously there's a bit of a problem there. So how do we go about solving this problem? Well, again, we just need to make sure that the range of f matches with the domain of g. So simply, we're just looking for the intersection of those two there. So we just need to make sure that the range of the y values coming out of f matches with the domain of the x values going into g. So if we look closely at the intersection at the moment, we can see that y can output any value, but x can only take values greater than or equal to 0. So what we need to do is we can't actually change this restriction on the domain of g, but we can restrict what comes out of f. And we want to restrict f such that the range of f is y is bigger than or equal to 0, because then the domain of g and the range of f match up perfectly now. But if we can restrict f so that we're only outputting y values greater than or equal to 0, then we don't have to worry about it fitting in with the domain of g and outputting some positive value for the range of g. But of course, if we're restricting the range of f to be y greater than or equal to 0, we're going to need to restrict the domain of f. Now, as it stands, y equals x plus 2. If we want the y value to be greater than or equal to 0, we need x plus 2 to be greater than or equal to 0, which means we need x values that are greater than or equal to negative 2. So by restricting the range of f, we actually have to restrict the domain of f first to allow this change to happen. What that means is that the domain of f needs to become x is greater than or equal to negative 2. This gives us a range of f, so we have y values greater than or equal to 0. They will all fit into the domain of g, which will give us all of the range of g. So what does that mean? That means that given our function g of f of x is the square root of x plus 2, this composite function is going to have a domain of x needs to be greater than or equal to negative 2. That's just to ensure that the range of f matches with the domain of g. And then the output for the function g of f at x is going to be y values are going to be greater than or equal to 0. Because again, we have the square root function, and that'll only output positive values. So in summary, for any composite function, we need to make sure that the output for the function we are substituting in matches the domain of the overarching function. Let's go through another example quickly. The question is, determine f of g of x and state its domain and range. What does that mean, f of g of x? That just simply means we want to substitute the g of x function into f. So in this case, f is x squared. So I need to substitute the g function into the f function. This gives me where the g function is x plus 3. So I'm just going to go x plus 3 all squared. So that's the function f of g of x. I'm substituting the g function into the f function. So that answers the first part of the question. We've determined f of g of x, but now we need to determine its domain and range. So what's going to happen is we're going to input values of x into g. This is going to output some y value for g. Then those y values have to fit inside f. And once we put those y values into f, we're going to get some new y value at the end there. So how does this look? Well, we need to write down the chain. So the first thing we need to do is we need to work out what's the domain of g. Now obviously g is a linear function, so we can put any value of x into that linear function there. So x belongs to the set of real numbers, and that'll output any real number because again it's a linear function. So we're going to put x values into g. That's going to output y values for g. Those y values of g will be put into the domain of f, and currently the domain of f is x can handle anything, and the range of f is going to be y is going to be greater than or equal to 0, because again f of x is x squared, which is a quadratic with a turning point at 0, 0. So that's going to be our f of x up there. Then we need to make sure that the output of g is going to match with the input of f. And in this case here, when we're looking for the intersection, we can see that the output of g does match with the domain of f. So we don't actually need to change anything with that respect. So what we end up with is the composite function f of g of x is going to equal x plus 3 all squared. The domain of f of g is going to be that bit on this side here. So the domain of f of g is going to be x is an element of real numbers. And the range of f of g is going to be the bit that comes out on the side here, which is going to be y is greater than or equal to 0. Now, when we look at this function here, that does make sense. It does make sense because this, again, is a quadratic. Quadratics can usually take all real numbers. And again, this is a quadratic that has been translated 3 units to the left. So all we've done is we've just translated the function 3 units to the left. And as you can see, y is still got to be greater than or equal to 0. What about g of f of x? So if we wanted to determine g of f of x, what we need to do is we need to substitute the f function into the g function. And again, the g function is x plus 3. So I need to put my f of x into the g function. So wherever I see an x, I'm going to put my f of x function, which is x squared plus 3. Now in this case here, we're going to be putting x values into the f function. So the domain of the f function, again, it's a quadratic, so we can put any real values into that function over there. And the range of the f function is going to be y is greater than or equal to 0. So I'm putting x values into my f function. Then whatever comes out of that needs to fit into the domain of my g function. Now the domain of my g function is x belongs to the real set of numbers. And the range of the g function is y belongs to the set of real numbers there. And again, we need to make sure that there is some overlap between these two here. So at the moment, the range of f, y can only be greater than or equal to 0, and the domain of g, x belongs to the set of real numbers there. And we need to look for some sort of intersection between these two. Now, we can't actually restrict the range of f at this moment. We can't change that. Doesn't matter what we do to the domain of f, we can't change this over here, but we can change the domain of g to match up with the range of f. We need to change the domain of g to be such that x is greater than or equal to 0. Now, if x is greater than or equal to 0, that means that the range of g, y, is going to be greater than or equal to 3. So what does this mean? This means that we have a g of f at x is going to equal to x squared plus 3. The domain of g of f is going to be x is an element of real numbers because we look at the side here, look at the far left, and the range of g of f, we look at the side here, is going to give us y values greater than or equal to 3. And again, when we look at the function, this does make sense. Because again, this is a quadratic and it's been translated 3 units up. For quadratics, we can accept all real numbers. And because this function has been translated 3 units up, looks like that, the y values have to be greater than or equal to 3. So this does make sense for this solution. Let's change g of x slightly now. And let's say g of x is the square root of x. And this is an important question because it highlights why we need to define the domain and range and make sure that they match each other. So determine f of g of x. Again, I'm not going to write it out as much as time. F of g of x means we're going to put the g function into the f function. So this becomes, we're going to put the g function into the f function, and it's going to become the square root of x all squared, which is x at this point in time. So we can assume that it's going to be a linear function. Let's just look at what happens when we do the domain and range now. We need to put x values into the g function. That'll output a y value from the g function, which will input into the f function, which will output a new value there. So the domain of g is x has got to be greater than or equal to 0 because we can't square root negative numbers. The range of g is going to be y is greater than or equal to 0. The domain of f is a quadratic, so we can accept any x values, and the range of f is y is going to be greater than or equal to 0. Again, we look at these two in the middle because these two need to match up. This is the link between g and f. Now we can see here the range of g, y is greater than or equal to 0, but the domain of f, x can accept any real numbers there. But because of this restriction on g on this side, the domain of f needs to change to match that. So x is going to be greater than or equal to 0 in this case. And if x is greater than or equal to 0, the range of f doesn't change either. The range of f is y is greater than or equal to 0. So what do we have? We have f of g of x equals x. The domain of f of g is whatever we have on the left there. So x is going to be greater than or equal to 0. And the range of f of g is going to be y is greater than or equal to 0. As you can see, normally we would expect this to be a linear line going through the origin, but we can't accept this part of the line. We can only accept the part of the line that's in the first quadrant. X is greater than 0 and y is greater than 0. Now, why does that make sense? Well, if I substitute in a negative value, let's say x is negative 4. Now, usually we could put in negative 4 into this function here, but just remember, we have to input that into the g function first. And as you can see, we can't actually square root a negative value there. We can't actually find the square root of negative 4. So all we're left with is the positive values of x, because we can only square root positive values of x. So this is still the line y equals x. However, we are restricted to only looking in the first quadrant. Let's look at what happens when we have to find g of f now. The g of f means we need to substitute the f function into the g function. So I'm going to get the square root of x squared, which is x. Again, let's set up the domain and range. So we're going to input x values into f, and then those will go into g. So we need to look at the domain and range of f first. So the domain of f is x is an element of real numbers. Because it's a quadratic, we can accept any real numbers. And the range of f is going to be y is greater than or equal to 0. The domain of g, x needs to be greater than or equal to 0. And the range of g is y is greater than or equal to 0. Now, when you look at g of f of x, we can see that these two match up. So the range of f matches up exactly with the domain of g. The domain of f was x is an element of real numbers, and the range of g was y is greater than or equal to 0. When we look at this function though, what do we notice? We notice that if we just take this as the linear function x, we should have y values that are less than 0, because the linear function of x looks like this. Again, that's y equals x. But here we're saying that x can be the element of real numbers, but the y values have to be greater than or equal to 0. So something else is happening here. It can't just be y equals x for the composite function. Let's look, we're putting values into f. Now when you look at f is a squared number, and squared numbers always have to be greater than 0. It doesn't matter if you put in negative numbers or positive numbers. So we need to look at what's happening with the f of x function, because x squared is going to do something quite interesting, and I'm actually going to look at this original function before we simplified it. So if I square root negative 4 all squared, that's just going to give me a positive 4. If I square root 4 squared, that's also going to give me 4. If I square root negative 3 all squared, I get 3. Because negative 3 squared is a positive 9. The square root of a positive 9 is a 3. And if I square root 3 squared, I get 3 again. You can see it doesn't matter if the x value is negative, it will output the same value as if the x value was positive. So what does that mean? That means that we don't want g of f of x to be equal x. It's actually going to equal the modulus of x. Because it didn't matter if I put in a negative 4 or a 4, it outputted only the positive value. And the modulus of a value always outputs the positive value there. So what does that mean? That means that our composite function g of f of x is, and the domain of g of f is x is an element of real numbers, because it's whatever we had on the far left after adjustments. But in this case, we had no adjustments. And the range of g of f is going to be y is greater than or equal to 0, which is what we had over there. Let's just look quickly at how that looks in the class pad. So if we go to main and we type in, we'll go to keyboard, we'll go to define f of x, and we'll define f of x to equal x squared. Good. And then we'll define g of x to equal the square root of x. And then we want g of f of x, so we can go g of f at x. And we can hit the button there, and you can see it gives us the square root of x squared. It actually hasn't simplified it down to the modulus of x for us. Now if I get rid of my keyboard, what I can do is I can go to my graph table function there, click and drag that down, and you can see it's actually given us the absolute value of x function. Now, I've been asked to explain question 20 from quite a few of my students. This comes from Sadler's textbook. It comes from exercise 3a, question 20. State the natural domain and the corresponding range of each of the following functions, given that f of x is x squared minus 9, that's a quadratic, and g of x is 1 over root x. And I'm only going to do part A with you guys. So when we look at part A, we want g of f of x. So we want to substitute f of x into g of x. So g of f of x is going to be 1 over x squared, take away 9. Now again, we're putting x values into f, and then f goes into g. So we need to look at the domain of f first. So the domain of f, f is a quadratic, so x is an element of real numbers, and the range of f is y is greater than or equal to -9. Then we look at the domain of g. The domain of g is x cannot equal 0, and the range of g is y cannot equal 0. And again, we're looking for the intersection of the middle two, because the range of f is what links us to g. We need the intersection of these two here, so we know that the range of f so far is y is greater than or equal to -9, but we also needed to include x cannot equal 0. So if y is x squared take away 9, that means that x squared take away 9 cannot equal 0, so x cannot equal plus or minus 3. And this makes sense, because if we put plus or minus 3 into g of f of x, we end up with it being undefined, because it would be 1 divided by 0. So far what we've got is we've got our g of f of x is 1 over x squared minus 9. Now, because we know that the domain of g of f is going to end up being this part down here, now we know that when we substitute x equals positive or negative 3, we're going to get an asymptote. So far what that looks like is, that's my x-axis, that's my y-axis. We're going to have an asymptote at -3, and we're going to have another asymptote at 3. Inside this range, we're going to have some sort of function. So between -3x and 3, we're going to have some sort of function inside there. Now, because we're squaring the x values, it doesn't matter if I'm doing the negative x value or the positive x value, they can actually give us the same value. So for example, if I square -2.9, that's going to be the same as 2.9 squared. So I'm going to ignore the negative cases for now, and I'm just going to know that it's going to be mirrored over the y-axis for the time being. So if I pick a number like 2.9, 2.9 squared is less than 9. So then we know that 2.9 squared take away 9 is going to be less than 0, which is just a negative number. That's all I'm determining there. It's going to be negative. It's going to be very small and close to 0, but it's going to be negative. And 1 divided by a -0 takes us to -infinity. So that means that as x approaches plus or minus 3, my y value is going to approach -infinity. So it's going to go down like that and down like that as it approaches inside this range over here. Then we need to think about what's the biggest number that we can get inside this range, because it's got to turn around at some point and go back down the other end. And that's going to happen when x is the smallest number, which would be 0. So when x is 0, the y value is going to be minus 1 over 9, because it's just going to be 1 over negative 9, which is minus 1 over 9. And that's actually going to be the largest value inside that domain between negative 3 and 3. What does that tell us? That tells us that between negative 3 and 3, my y values are going to go from negative infinity all the way up to and including negative 1 over 9. Now let's look at what happens when we go more positive than 3 or more negative than negative 3. So let's get close to 3 now. Let's pick a number that's just a little bit bigger than 3. Say, for example, 3.01. That's just a little bit bigger than 3. We know that 3.01 squared is going to be bigger than 9. It's going to be bigger than 9, so when we do 3.01 squared, take away 9, that's going to be a positive value. And it's going to be just a little bit bigger than 0. It's going to be a little bit bigger than 0, but not much bigger than 0. So we're still going to have 1 divided by 0. And 1 divided by 0 is going to be undefined or infinity. So as x approaches 3 from the right, we're going to go up towards infinity. Because we're going to be doing basically 9 take away 9, but it's going to be just a little bit bigger than 0. And then again, this will be mirrored on the negative side, because when we square the negative, it's going to turn into that positive anyway. Then we need to think about what happens when we pick very large numbers like infinity. So infinity take away 9 is infinity, and 1 divided by an extremely large number goes towards 0. So as x gets very, very, very large, the y values are going to go towards 0. And again, that's going to be mirrored on the left-hand side and the right-hand side. So this is what the function is going to look like. So how do we put all of this together now? Well, we know that when x is between negative 3 and 3, y is going to go from negative infinity to negative 1 over 9. And for x being less than negative 3 or x is greater than 3, we know that the y values are going to go from 0 all the way up to infinity. Let's just put that into context now. So we can write the domain of g of f is going to be x can't equal positive or negative 3. Those are the only restrictions on the x values there. And the range of g of f, well, it can go from negative infinity to minus 1 over 9. That's the first part of it. But the y values can also go from 0 to infinity. The only gap we're missing is between negative 1 over 9 and 0. That's the only bit it can't actually equal. It's a small gap inside there. That's the range of g of f. So it goes from negative infinity all the way up to negative 1 over 9, where negative 1 over 9 is up here. And then it can go all the way from 0 up to infinity.